Hey everyone and welcome to PrepFusion. I'm Anish and today we'll be starting the lecture 13 of this time domain analysis. We're almost at the end. Okay, this will be the question lectures again, assignment questions basically, and I will take another lecture while I will give you the whole summary of what happened throughout the chapter and what things you have to keep in mind and what things you can skip basically if you don't understand that, right? So basically you don't have to understand everything, just the main thing is questions should be solved. That's how you crack the exam, right? Obviously I have tried my best to give you all the concept and clarity. Why is this formula being used, why is this being used? Okay, but even sometimes it may happen that doesn't come to your brain at that instant, but it may come to your brain, like you may understand that after a while. Okay, but you don't have time, you have to crack the exam obviously now. So that's why you try to solve the questions. For solving questions, all the concepts don't need to be cleared, okay, obviously, but most of the concepts needs to be cleared. Okay, but you need to see how am I solving the questions. So like you first pause the video, right? Whenever I bring some question in front of you, pause the video and then you try to solve it yourself, then check the answer with me. Okay, so this is the first question. Okay, so what is the first question telling us? First question is, for the given closed loop control system, the values of Kp and Kd are such that the system has damping ratio of 0.6 and natural frequency of oscillation of 5 radians. Now where is Kp and Kd? Kp and Kd is basically here, right? Okay, so and the system also, so the Kp and Kd values are set as such. My system has damping ratio of this and natural frequency of oscillation of this. So it is a basically second order system under damp that we got from this question, right? Okay, then what do we have to do? Like we have to find the values of Kp and Kd basically. That is what we want to set the values of Kp and Kd so that my system has damping ratio of this and omega n equals to this, right? And also we have to find, after finding this Kp and Kd, right, we have to find the steady state error for the unit ramp input. So this is the system. Okay, take the pause the video, take the screen, whatever you want to do, then find the value of Kp and Kd such that my system has omega n of 5 and zeta of 0.6, right? Yeah, so then you find the steady state error for unit ramp input, right? So yeah, now I will solve this question. So what will be the solution basically? So first what I will try to do is find the CLTF, right? Okay, because by finding the CLTF I can compare my omega n and zeta, right, with the characteristics equation. So what will my CLTF, what transfer function? T of s will be simply g upon 1 plus gh. Now what is g? G is this one, right? G is, okay, where did I go? I go into someone previous. G is this one, okay, G is this one. So this will be Kp into s plus 1, okay, Kp into s into s plus 1 divided by 1 plus Kp into s into s plus 1 into 1 by 1 plus Kd into s. So Kp plus Kd into s. Okay, so this is basically my transfer function. Now let's tidy this one up, right? Simplify this one. So I will multiply by s into s plus 1 for numerator and denominator. So this will become Kp divided by s into s plus 1 plus Kp into 1 plus Kd into s. Now let me convert this into my standard form, right? So what is the standard form? So let me write in white only. Okay, my transfer function equals to Kp this will be s square plus s into k, this one I will multiply here, so this will become, here I have also 1 here, okay, this s has 1 here and this is Kp times Kd, right? So 1 plus Kp Kd, okay, plus this one is basically the constant number is equals to Kp itself because the dc is 1 here, right? So e plus Kp. Okay, so now I will compare with this my standard equation. What is my standard equation? So standard equation is s square plus 2 zeta omega ns plus omega n square equals to 0. So this is my standard equation. Okay, so now right now, so from here I can find my omega n square equals to kp, right? Okay, directly compare this one. So what is my omega n square? Omega n, they have told us, is 5 radians per second, so it will be 25. So kp will be basically 25, right, as omega n is 5 radian per second. Okay, now what is my kd equals to? What is my kd equals to? So I can compare this one with 2 zeta omega n, right? So my 2 zeta omega n will be equals to 1 plus kd, right? So zeta is what, 0.6, okay, and omega n is 5, and this is 1, plus kp is again 25, okay, and into kd, right? Kd is what? Kd is simply kd only. I have to find the kd, right? So now what should I do? Simply I should write kd equals to this becomes 10, 6, 5, and I have to divide by 25 also, right? Okay, divide by 25 also. So my kd will be 1 by 5 basically, okay, and kp will be simply what do you say, 25, right? So this will be equals to 0.2, okay. So kd will be equals to 0.2 and my kp will be equals to 25. So this is, okay, let me write, kp will be equals to 25 and kp will be 0.2. Now what do I need to find? I need to find the steady state error, right? So for steady state error, what I can do is, one thing I know, okay, at like DC, right? DC, this h of 0 is going to 1, right? So I can simply apply the that unity feedback formula, okay, that I can apply, okay. Else if this was not going to 0, I would have to apply the other formula where h of 0 is not equals to 1, right? So this one was the what? This one was the 25th question. And this is the 26th question. Okay, 26th question. So now I will take this one, okay, and I will say that my h of 0 is going to 1, right? My h of 0 is going to 1. So if my h of 0 is going to 1, then what can I say? I can simply use that error formula. So what will my steady state error equals to? So my steady state error E of ss equals to limit s tending to 0 s r of s into 1 minus transfer function, right? That I can use, because like g into g of s I can use, because this is not unity feedback exactly, right? That's right. But this becomes unity feedback at s equals to 0. I can use that formula also, but let's use this. I know my transfer function, right? What is the transfer function? Transfer function is this one, okay. I'll just replace my kp and kd here, okay. Or transfer function they have anyways given us, right? How? By telling us the omega n and the zeta, right? So I can write it directly here. What is my s r of s? So r of s is what? It's a unit ramp input. So if for a unit ramp input, this is s, okay, and limit as s tends to 0 into 1 over s into 1 minus transfer function. What is transfer function? Omega n square, which is 25, right, divided by s square plus 2 zeta omega n, which is 2 into 0.6, okay, which is 1.2 into 5, which is equals to 6 itself. 6s plus omega n square again, okay, and I need to put s equals to 0 over here. Can I put s equals to 0 over here? Oh, this is s square, sorry, this is s square, okay. Now what is happening after simplifying? Now we can simply put 0 over here, okay. First we need to simplify, because this s will get cancelled, but there will be still one s remained here. So let me first simplify this inner function. So What is this? This is limit as s tending to 0. I have still one s in the denominator, and if I subtract this one, right, subtract this one, this will be s square plus 6s plus 25 minus 25 divided by s square plus 6s plus 25, right? Now what is happening? This limit as s tending to 0, I have 1 over s over here, right? 1 over s over here, okay, and this is s into s plus 6 divided by s square plus 6s plus 25. Okay, so what is this? This s will get cancelled, and this will be s plus 6. Okay, so now I can put s equal to 0. Now I can put s equal to 0. So what happens if I put s equal to 0? Sorry, this was this 6? Yeah, this was 6, right? Yeah. So if I put s equals to 0, what do I get? I get that it is 6 by 25, right? My error is 6 by 25. So what is 1 by 25? It is 0.004. So 6 is 0.024. So this is basically my steady state error. Okay, so now let's go to the next question. What does the next question tell us? So next question is asking us to find is which of the following will have the highest maximum peak overshoot and the minimum peak overshoot for a unit step. I mean, we have to not the lowest, okay, lowest peak overshoot, I should say, because like peak overshoot can be anything. So out of the, okay, where did I go? Why is this going back? I don't understand. So out of the following 4, right, we have to choose which one has the highest peak overshoot and which one has the lowest. So first let us do it using induction method. Then what we'll do, we'll basically solve this, right? So what does my maximum peak overshoot depend on? What was the formula? It was e raised to power minus pi cot theta, right? Minus pi cot theta. Okay, now again I can write it in terms of zeta. It was zeta by under root 1 minus zeta square. Okay, so if from that what I can understand, if my zeta increases, then my maximum peak overshoot will reduce, right? Reduce. Why? Because it was e raised to power minus some zeta square. So if zeta by under root 1 minus zeta square increases, then it is minus, so my exponential power will reduce. Okay, so my MPO will reduce if my zeta increases. So can I understand from here, is my zeta increasing or decreasing? I can, right? Why? Because my omega n is same for everything, so only my zeta is varying. So comparing all these 4 are very easy, right? So now what I can say is that omega n is constant, right? So here, as this term is equals to what? This is equals to 2 into zeta omega n. So out of them, whichever one will be the lowest, that one will have the lowest, that one will have the highest peak overshoot, maximum peak overshoot, because if zeta is high, then MPO will be low. They are inversely proportional to each other. So method 1 is basically zeta, MPO is inversely proportional to the zeta. MPO is inversely proportional to the zeta. Okay, so this is my method 1. So now so what do you see? So which one has the highest zeta? That one will have the lowest peak overshoot. So highest zeta has this one, right? Okay, and is this familiar? Is this equation familiar? This is like the s plus 20 whole square, right? S plus 20 whole square. What does this mean? This means this is this has same negative equal roots on the axis, right? Negative real equal roots, okay, on the sigma axis. That means this is a critically damped system. Now what is the main thing that for critical damped system? What are the characteristics for a critical damped system? It has no overshoot, right? It directly reaches its steady state directly, okay, and very fast, right? So from here also I can understand, yes, for critical damped system there is no overshoot, so this will have minimum overshoot, because for critical damped system the overshoot is 0. That also we derived in our previous lecture, right? Okay, so D will be have the lowest. Okay, now which one has the lowest zeta? C, right? C has the lowest zeta, but also we have to check, is this underdamped or not? If this is not underdamped, then this will be an issue, right? Okay, but if I check from here that my omega n is 20, okay, and 2 zeta omega n is 10, So if I divide it by that one, so this will come out to be less than 1. Okay, then it is fine. Okay, so yeah, then this is fine. Now like this, if this increases, then only my zeta will increase. Obviously this will be underdamped, but I have to check for undamped system as well. Check if this is undamped. When will this be undamped? When the coefficient of s will be 0. Okay, if the coefficient of s is 0, then this system will be undamped. And then what will happen? What will happen from MPO? MPO will be maximum, right? It will be 100%, that we solved previously also. So for undamped it is maximum, for critical damped it is minimum, so for underdamped it is somewhere in between, right? Okay, so I am somewhere in between. So this is the this is the least MPO. Now this is the maximum MPO. Then I'm coming over here, and this is the this is a lesser MPO than this one, than C, and this is lower than that one, and this is the lowest one, basically 0, right? So yeah, like this intuition directly from seeing the options you can say. But let's calculate. Okay, from options I will say, like from options. Okay, but now what is the method? To simply write the MPO for each of them, and then there you will understand. So what is my omega n? Omega n is 400, right? So omega n square is 400, so omega n equals to 20, right? So omega n equals 20 radian per second. Okay, so now compare for each of them. So let's compare the first. So this is my zeta to zeta omega n. So what is my 2 zeta omega n? It is basically equals to, for the A it is 20, right? 20. So what will be my zeta? It is 10. Omega n is divided by 20, so it is simply what do you say? Okay, 2, 10, and it is also 20, so this is 1 by 2. Okay, so this is my zeta for the first case. Okay, then for the second case, what is my zeta? It is basically 30. So again I will write in this one, 2 zeta omega n equals to 30. So this is this cancels it out. This is 1.5 by 2, this is 0.75, right? So this is zeta equals to 0.75. Okay, now what is for the second case? So for the second case, right? Okay, I don't have space for, so for the third case, sorry, C, for the third case I have 2 zeta omega n equals to, I think it was 10. It was equals to 10. So basically zeta equals to 2 into omega n. What is omega n? Omega n is 20, so it is 1 by 4, so this is equals to 0.25. So here, right, the zeta is minimum. If zeta is minimum, what I can say? That my MPO will be maximum. Okay, hence this one will have maximum MPO zeta minimum. Okay, and now what about D? D is 2 zeta omega n equals to, what is this? This is equals to 40. So this is basically critical damp, as I can see from here also, that this will come out to be zeta equals to 1. So what does this mean? This means zeta is maximum, hence minimum MPO, right? Minimum MPO. Okay, so yeah, basically that is the main case. So what are the edge cases? So what are the edge cases? Edge cases are, as we remember also, that for critically damped, okay, critically damped, for critical damped my system will have minimum MPO, right? No, basically no overshoot. So no overshoot. Okay, and for undamped, right, it will have highest overshoot. will have highest overshoot. Okay, so yeah, that is basically the crux of this lecture, right? Okay, I mean not the lecture of this question. Okay, let's I think you have got the understood the concept of this question. So let's go to another question. So in this question, right, we have to plot the unit impulse response of the given block diagram. So we have to plot the unit impulse response of the given block diagram, right? So we've been given the block diagram and simply just plot it. So it's very easy, right? Simply we can find the transform function, and from there we can just take the Laplace inverse, and that will be my unit impulse response. So this is the chapter 1, okay, or chapter 2 you can say, okay, but I don't know, this is just a bit of difference that we'll see. Okay, so but in chapter 1 you just can't simply take the Laplace inverse, that will be difficult, but here you can't. Why? We'll understand. So basically, right, I will just simply solve this with the help of block diagram. How you can solve, right? So this is my C of S, right? This is my C of S. So here I have C of S, okay, here I have C of S. Let me write here I have C of S, and here I have, let me name this as X, right? Let me name this as X. Okay, I will just not write S here up now. I will just ignore the S. I will write X here and C here. So what will this become? This will become basically X plus C, right? This will become X plus C. Okay, so okay, this will become X plus C. What I can do is, okay, what I can do, if this is X, right, then what is this? What is this? Basically this is X into 1 over S. This is X into 1 over S, that is X by S. So I can write here directly X by S instead of C, so that I can get in terms of one variable only, one unknown. So this will be X by S, okay, and this will be X plus X by S. Okay, what does this become? This is R of S. So this becomes R minus, here this becomes R minus X plus X by S. Okay, so this is this one. So now if I multiply 1 by S with this one, I should get X again back, right? So that is what exactly I will write in the equation. So R into X plus X by S into 1 by S equals to my X, right? So what do I get now? So I will write X in terms of R. So this one will be R only, and I will take this 1 over S on that side. We'll take this 1 over S in that side. So this will be Sx plus X by S. Okay, so this is R into X into S plus 1 over S. So this is equals to, so my X will be equals to simply S will go over that side, SR divided by S square plus S plus 1. Okay, so yeah, this is basically what my X is equals to. Now, right, now let's write in terms of C. What is my C of S? C of S is this one, right? X by S. So C of S is X of S by S simply. So now I will put that in the equation. So my C of S will be, which is divided by S. So what will this become? This will be S. S will be divided. S is also in the numerator. So it will become R of S by S square plus S plus 1. Now C by R is transfer function. So my C of S over R of S equals to my transfer function, which is 1 over S square plus S plus 1. Okay, so now, right, so is this familiar? Is it familiar? What I can see, what I can observe here, I can observe like this is a single order system. Okay, so there will be some damping involved. So what I can observe is my omega n is 1 radian per second. Okay, and my what is zeta? 2 zeta omega n equals to 1, and zeta equals to 1 by 2. So this is a underdamped, right? Because zeta is between 0 to 1. Okay, so this is a underdamped. Underdamped. So this is underdamped basically. So yeah, this is underdamped. Now, right, now so can I draw the impulse response? So what is the impulse response for an underdamped system? Just try to remember, right? I hope you remember during the first few cases we derived. What was it? It was basically there were oscillations and it ended at 0, right? It ended at 0. So how will my impulse response look like? So my impulse response will look something like this, right? It will start off oscillating, and it will go to 0, right? So this is how my impulse response of okay, C of t will look. C of t is simply unit impulse response. Okay, unit impulse response. You can find the MPO, everything, because we know the zeta. Okay, and this is 1 only. Okay, so like steady state will go to 0, but we can find the MPO, all those things, but that is for a unit step response. I hope you remember, right? This is for the unit impulse. Okay, so for this I have to just write the expressions here, then I can find it. So yeah, that is the important thing. So yeah, I think that is it for this question. Let's go to the next question. So the next question, we have been asked to, for the system shown, if my KD is equals to 0, find KP if, okay, if the not the steady, it needs to be steady state error. Steady state error for the unit ramp is 0.2. Steady state error for the unit ramp is 0.2. Okay, so yeah, for the system shown if my KD is equals to 0, find KP if the steady state error for unit ramp input is 0. So firstly we have to find this KD, then I will read the next question. Okay, so let's first solve for 29. Let us solve 29. Okay, so how to solve this one? So we know that the for unit ramp I'm getting a finite error. Okay, so that must be the case that like this overall thing, right? This overall thing has to be of type 1. Okay, because obviously this is not unity feedback, but if I convert this into one block, this has to be type 1. So what I will do, I will try to convert this into one block first. So I'll copy this one. Okay, if I copy this one, and like how to convert this into one block, write the equivalent transfer function. So what is the equivalent transfer function? Equivalent transfer function is 2 upon s into s plus 2 1 by g upon 1 plus gh. So 1 plus KD. So I have KP also, that I will write later on. So this will become, okay, rotate it too much. So this becomes simply this one, right? So what I can observe from here is this is a type 1 system itself. So now this is converted to this one. So I will again, what I will do, I will just delete this one and this one. Okay, remove this adder and convert this into a single block itself. Okay, and this becomes simply 2 upon s into s plus 2 plus 2s KD. Okay, plus 2s KD. Now again, right, I can convert this into one block again. This will get simply multiplied. So what I can do, I can remove this one and make this a single block itself. This will be KP. Okay, so what I can see, this is a type 1, right? If I take the s common, so I will again simplify this one. I will take the s common and this will become s s plus 2 plus 2 KD, right? Plus 2 KD. plus 2 kd. Okay, so this is basically my equivalent transfer function, right? Equivalent transfer function. So okay, what I should do is, let me copy this one actually and paste this one over it, because student who will read the notes, they will not understand what happened over it. So okay, I can't even go to back. Okay, I need to cut this, right? Put it like this one. Yeah, like this one. Then I need to paste over here. Yeah, now I think students will understand how I changed the block diagram, right? So this is the modified block diagram, and for this one they have given me the unit steady state error for unit ramp input. Okay, and kd, okay, my kd was equals to 0. Okay, so I didn't notice that one. So anyways, I will need this in the next case. So my kd is equals to 0. What will this become? So this will become simply, I will again copy this one. Okay, s by only this s plus 2 will remain, right? S plus 2 will remain and this will go away. Okay, okay, so now what will happen? Now basically I have to find the velocity error coefficient. Okay, that is what the ramp, and for the ramp input the error is. So what is my velocity error coefficient? My velocity error coefficient is kv is equals to what? This s times limit as s times 0 s times g of s, right? Okay, what is equals to? So this is equals to 2 kp upon s. Okay, 2 kp upon s into s plus 2 into, I have s also here, right? And this is limit s tending to 0. Okay, so now if I cancel this one out and put s equals to 0, what do I get? I get 2 kp over 2 itself, which is equals to kp itself, right? So which is equals to my 0.2, right? Steady state error. Okay, so yeah, my velocity error coefficient equals to this one. So if you just simply write this one with flow, you will go wrong, right? Why? Because this sometimes happen in exam also. We make some silly errors, and this is one of them. So we make kv equals to my steady state error, but it is not, right? My steady state error ess equals to 1 over kp, right? My steady state equals to 1 over kp. Okay, so now what will be my kp equals to? So I mean, sorry, not 1 over kp, 1 over kv. So what will my kv equals to? Kv equals to 0.2. So this is equals to 5, right? So this is equals to 0.2. So this will be equals to 1 over 0.2, not the other way around, because 1 over kv equals to steady state error, and my steady state error is 0.2. Okay, so yeah, kv equals to 5. So this is my kv. Okay, now I found my kp also. Kv is equals to kv itself. So now let's solve for the second case, right? So first case is done. Kp equals to 500. Kp equals to 500. Okay, so what is the second case? The second case is, what will be the new value of kp and kd if the damping ratio made is 0.5 without affecting the steady state error? Okay, so what will be the new value of kp and kd if the damping ratio is made 0.5 without affecting the steady state error, right? So I have to choose kp and kd, and my steady state error should remain same. That is basically for a unit ramp, that is because this will always be a type 1 system, as found out from here, right? Always be a type 1 system. So I have to choose my kp and kd such that my damping ratio is 0.5. So what I will do, I have found out this one, right? So I can find my transfer function, and from there I can find my from the characteristic equation I can compare these two, right? And from there I can find my kp and kd. Okay, so what is my transfer function? Transfer function is simply this one. Okay, this one, g upon 1 plus gh. So this is, again I will copy this one, 2 kp upon s into s plus 2 plus 2 kd divided by 1 plus 2 kp upon s into s plus 2 plus 2 kd. Okay, this is my transfer function basically. Okay, so now right now what will my transfer function equals to? It is basically 2 kp upon s into s plus 2 plus 2 kd plus 2 kp again, right? 2 kp. Okay, so this is my transfer function. So now what do I need to do? Equate this with the characteristics equation. So what is my characteristics equation? It is s square plus 2 zeta omega ns plus omega n square now equals to 0. So what is my zeta and omega ns? They are telling. So zeta is 0.5. okay, omega ns I don't know. Okay, omega ns I don't know. So like from here I have to find the one relation between the steady state error also. Steady state error they have given us 0.2, right? Steady state error they have given us 0.2. So my steady state error equals to 0.2 itself again, right? So which will be equals to again 1 by kv. So what is my 1 by kv basically? 1 by kv is this limit s tends to 0 as g of s. Okay, this is 1 divided by and so what is this? 1 divided by this s into this one. Where did I go? This was my g of s, right? So multiply s with this one. What am I remained with? I'm remained with, okay, let me do this like this only. So okay, I will not solve it. I will just do what is this equals to. Let's see, you will get confused. So s into g of s equals to, this is my g of s, right? This is my open loop OLTF. This is my OLTF, right? This is unity feedback system, and this is my OLTF, right? So what I can do is multiply s with this one. So what I'm remained with is limit as s tends to 0. If I multiply s with this one, this s will get cancelled, right? Then I will remain with 2 kp by s plus 2 plus 2 kd. So 2 kp by s plus 2 plus 2 kd. Okay, so what is this? S equal to 0. This is equals to simply 2 kp by 2 plus 2 kd, right? So this is equals to 0. This is not equal to 0. 1, sorry. So this is basically equals to kp by 1 plus kd. Now I will put this over here, and this will be equals to my 0.2, right? So point 2 will be equals to simply 1 plus kd by kp. Okay, so my kp will be equals to 1 by 5. So this is 5 times 1 plus kd, right? So I can equate it like this one, right? Now let's solve for this equation, right? Solve for this equation. So what do I know? I know that my zeta is what? Zeta is half, right? Zeta given is half. Okay, so if zeta is given is half, so my 2 zeta omega n. Okay, I need to my 2 zeta. I need to like simplify this further. Actually, I forgot to simplify. This will be 2 kp divided by s square plus 2 kd into s plus 2 kp. Okay, so yeah, this is basically my t of s, right? T of s. So now I can compare my 2 zeta omega n as 2 zeta omega n should be equals to 2 plus 2 kd, or I can take the like, okay, I will not take the common right now, or I don't have space, but still what I will do, I will push this one over and push this one over also. Okay, so my zeta omega n equals to simply 1 plus kd. And what is my 1 plus kd equals to? 1 plus kd is equals to kp by 5, right? Okay, I need to put here 1 plus kp by 5. Okay, so replace this. Okay, this is my equation 1. Okay, so this is my equation 2. Basically put, let me write this better, put 2 in equation 1, right? So if I do that, then what will happen? Then basically my kp by 5 will be equals to like this one, right? Zeta omega n, and zeta is half into omega. Now what is omega n equals to? My omega n is equals to, okay, let me not take this into the next page actually. My omega n is equals to 2 kp, right? Omega n is equals to 2 kp. Is this true? No, right? So omega n square equals to 2 kp, right? Omega n square. So this will be omega n square equals to 2 kp, and my omega n equals to under root 2 kp, right? My omega n equals to under root 2 kp. Okay, so this is my what omega n is equals to. So I can replace my omega n over here, right? Zeta I have replaced already, so I will replace my omega n, what is equals to, it is under root 2 kp. So now what I can do, I can simply take the square, but before that let me do a simple simplification. So this will become, I am dividing by 2, this will become kp by 2, right? So now I can do simple simplification, that is squaring on both sides. So if I square on both sides, right, so kp square equals to 25 equals to kp by 2. So my kp will come out to be 12.5. Now from here I can derive my kd also. So what will my kd? So I know 1 plus kd equals to, or it was, what was it? It was, I think, where was it? Where did it go? Yeah, 1 plus kd. Okay, no, not here. Yeah, 1 plus kd into 5 was equals to kp, right? So this will be kp by 5 basically. So 1 plus kd equals to 2.5 and kd equals to 1.5. okay, kd equals to 1.5, kd equals to 1.5. okay, so this is my answer. This is my answer basically. This is one of the answer, and this is the another answer, right? This is the another answer. Okay, so these two are my answer. So I have to understand how I did it. Obviously for the first question, right, you don't need to like derive this block diagram, okay, because my s is 0, like sorry, my kd is 0 for the first case. My kd is 0. I like forgotten that, but anyways I needed to do this for this question, so I done it like that only. But if you know the kd is 0, right, what do you do? This is 0, this is gone, right? This is gone, so this adder will, subtractor will also be gone. Simply this will become kp into 2 by s into s plus 2. From there you can directly equate and find the value of kp very fast. Okay, but if kd is not given, kp is not given, then you have to solve it like this one, right, as I solved. Okay, so have you understood, right? So yeah, that is it for this question. This time domain analysis, right, this is not that much of a big conceptual subject as per se, just formulas and practice. Okay, just you have to do formulas and how to put it in the equation, and few things are just basic conceptual, but it's not like state space, right? State space is like conceptual also, and like there are not much formulas, but you have to understand everything what is happening, right, about the observability of the controllability, all those things, right? So it is very important. So two are a bit different. Time response, it I think a bit easier. Just remember the formulas and you are good to go, right? So yeah, this is for this question. Let's go to the last question basically. So what is the next question telling us? We haven't given that the system is stable. Okay, system is stable, and we have to find the kp, like sorry, no, we haven't given the kp and ki, all these coefficients were given, right, for all of this, but we have to find the z of infinity. Where is z? Z is here, and we have to find the steady state value of z. Okay, then how should you proceed in these types of question, right? So firstly, the simplest method will be just simply put all this value here, then find z in terms of my rt, right, and then put the value of r of t, then use the final value theorem. Okay, but gate also wants you to do like that. But what is the issue with doing like that? The problem is it will take time, it will waste your time, right? If you put values over here and then calculate, all that thing will take time. So how should you solve this question? What you should do is basically write this in terms of this expressions only, and at the end stage you put your values of ki, kp and all those things. Here also what you do, as we need to find for steady state, what I will do, I will just put this as t of s. Okay, I will just put this as t of s, then at the end I will simplify. Not here, I will not simplify. Okay, let me write, then I will understand what I am trying to tell, right? So this will be simply, I will write this one as t of s only. Okay, I will write this one as only t of s, so an unknown. Okay, so I will not put values over here. But now what I will do, this will be easier for me to solve using the block diagram reduction technique. I just want my z value, right? Then at the end I will apply final value theorem. Then at the end I will put this ki, kp, all these values. Okay, and check if something is cancelling or not. So my z into t of s, okay, and like at this end, what is my value? This is z into t of s, right? So z into t of s, and what is this value? This is okay, I will write this as r of s. Okay, I will do the Laplace inverse of this unit step at the end, right? At the end. So this is r of s. Let me write this in a better manner actually. Like r, this, what will this point be called? This point will be called simply r of not this point, this will be called z into t of s, and this is r of s. So this point will be called r of s minus z into t of s, right? So this point will be called like this one. Okay, so yeah, this one will call this one. Now if I multiply with this one and this one, then add these two, I will get back my z. Okay, I will write that only. So I will do that only. So my r of s minus z t of s into this whole transformation, right? This one. Okay, this is the adder. So this is basically my ki over s plus kp. So this will be equals to my z itself, right? Now I will just simplify. Okay, I will just simplify. What I will do, this one will be, I will not write s right now, this is z times t. Okay, this bracket is I'm just ignoring. Okay, so this will become ki plus kp of s equals to zs, right? Now what I will do, I will take this one as r into ki plus kp of s. This will go to that side, z of t will go to that side. So if I take the z of common here, and this will be t of s, right? And this has also, okay, this has also this term, right? So I will take this and was common, and what I will do is into ki plus kps plus s. So now, right, now I can use the find the expression of z of s. What is z of s? Z of s equals to my r of s divided by t of s into, why am I not putting t of s like here? Because I will put it at the end, right, when I will use the final value theorem. So this is ki, to check if something is cancelling out or not, kp of s into s, and okay, this one is this one, and this is ki plus kp of s, right? So now what I will do, I will use the final value theorem. Okay, so my z of infinity, final value theorem basically. Okay, my z of infinity, let me write this in different pen. Z of infinity is basically equals to s times zs limit s tends to 0, right? S tends to 0. So this is my final value theorem. So this is my final value theorem. This is 1 over s, and like r of s is 1 over s only, and this is s times ki, ki plus kp over kps divided by limit as s tending to 0. And this is basically t of s times this thing ki plus kp of s plus s itself, right, plus s. So this is s. So now I can put s equals to 0. So if I put s equals to 0, what do I get? So my z of infinity will be equals to, if I put s equals to 0, this one will be 1 only. Okay, here can I put s equals to 0? Okay, this one will become ki only, right? So this one will be ki only, right? And in the denominator, what is happening? Denominator. So if I put s equals to 0 over here, this doesn't, okay, where did I go? This doesn't have any poles at s equals to 0, right? So there won't be any cancellation. So what is my t of 0 basically? T of 0 is 1. As you can see, t of 0, if I put, it will be omega n square by omega n square. So this will be 1 only. So t of 0 will be 1 only. So this will be 1, okay? And this again becomes ki, and this also becomes 0, right? Because this is s simply, this is simply s. So I should write this in a better manner. This is s and s, okay? So this also becomes basically ki only and plus 0. So what does this become? This becomes only 1, okay? This becomes only 1. So yeah, this is what my z of infinity is equals to. So what do you see? That ki and getting cancelled, okay? And whatever the values of ki, kp and omega n and zeta, whatever the values of them are, so this is actually omega n, okay? This is not omega simply, this is omega n, okay? So whatever the values may be, it doesn't matter, right? It doesn't matter. They just are cancelling each other out. That's why you shouldn't put all the values at the start. You should put all the values at the end. You just assume some variable, like I assume like it has t of s. I can assume anything, right? Then at the end, as I know, why did I do it? Basically I didn't need to find any generalized expression. I just need to find some value at some point, right? That's why I did it, okay? I did 0 of infinity. So yeah, basically that's what I did, and I found my 0 of infinity from equals to 1, okay? So yeah, I hope you understood the concept why I did this, and like this one, right, you will solve this much faster. But IIT wants you to do like the first one. What you put all the values, okay? They will give you some over information. You put all the values and then finally solve and get the answer as 1, okay? But if you solve like this one also, this will also give you same answer, and this will be much more cleaner and much more time efficient, okay? So that's how you should solve these types of questions. So yeah, thank you for watching, okay? And I will see you in the next lecture. That is a summary for time response analysis. Thank you.